Hello, my name is Maciej Pijanowski, and the topic of my presentation is overview of secure boot state in the ARM-based SoCs. Let's start with the agenda. At first, I'd like to introduce myself and my company. Then, I will explain what do we mean by secure boot in the context of this presentation. Next, we will discuss the typical secure boot implementation and workflows. After that, we will present results of the secure boot availability research on different platforms. At the end, we should have a few more minutes for questions. My name is Maciej Pijanowski. I'm boot firmware team leader at FreeMDeb. I'm with FreeMDeb for 5 years already. I'm interested in embedded Linux, build systems, mostly Octo, and system security. If you would like to contact me, you can use email or find me on social media listed there. I'd like to share a few words about FreeMDeb first. FreeMDeb is an embedded systems consulting company. We are based in Gdańsk, Poland. One of our main goals is to promote and improve the open source solutions on the firmware and system level. Our team is mostly specialized with the UEFI, Core Boot, Linux, Yocto, and so on. Many of our solutions are from the platform security area. Let's explain first what do we mean by secure boot in the context of this presentation. We are focusing on the ARM devices only. The secure boot is a term used by vendors for a specific BootROM feature. Potentially, the term verified boot would fit more here, as the main goal of this feature is to verify the firmware before executing it. The signature of the loaded firmware is verified. During the process, private key is used to sign the firmware, while the public key is used to verify the signature. In that scenario, we are assuming that the BootROM is trusted, although some of you may disagree with that, given that, in all cases, the BootROM is a proprietary piece of code which we cannot control. The meaning of secure boot may be different in case of different architectures or in different contexts. Now, I will present the typical implementation of the secure boot. The most common way of storing the public key is to write it into the SoC in a persistent manner. Usually, the fuse, so the electrical fuse, or other form of one-time programmable registers are used for that purpose. The public key, persistently written into the SoC, will be the root of trust of the verification chain. The first component is verified by the BootROM using the public key fused in the SoC, while the following components could be signed with different keys. In this case, we will be focusing only on the first step, so only on the verification of the first binary loaded by the BootROM. The typical workflow can look as follows. At first, we need to generate the key pair, so a private and public portion of a given key. In a secure location, the private key can be used to sign the binary. The public part of the key is then fused into the SoC. Once we confirm that the verification works correctly, we can lock the platform so only the signed firmware can be allowed to be executed. Locking the platform is usually also done via blowing a particular fuse. Let's also briefly discuss what does it mean to sign the firmware binary. Usually, the binary data is extended with some form of header. The header format is specific to the given secure boot implementation, and it can be different in case of any vendor. The common part is that the digital signature of the binary data is one of the main components of the header. Now, we will discuss the state of the secure boot feature in some of the ARM SoCs. We will start with the IMX family from NXP. In this case, the secure boot feature is called HAB, so the high assurance boot. It can work with up to 5 different keys, and it supports multiple types of keys, both RSA and EC keys. An interesting feature is that the HAB can be used to verify more than one binary. For example, we can use HAB API in U-boot to verify the kernel image directly using the HAB feature and public key fused inside the SoC. So a single key could be used to verify all of the components in the boot chain. The application notes describing the HAB usage are freely available. The most useful ones would be the AN3581 and AN1226-3. There are also lots of guides online describing how the HAB can be used in practice. The SoC reference manual can also be obtained, but it requires a free registration on the NXP site. The code signing tool is also available after a free registration. It can also be used with HSM devices, which is described in another application note. At that point, it is important to remember that the vulnerabilities in BootROM may also happen. One of them was found in the HAB a few years ago. So when using it, make sure that your device is using the patch to BootROM. Next, we are moving to another SoC family from NXP, the Layerscape. In that case, the secure boot is one of the features of the Core IQ Trust architecture, which is implemented in most of the Layerscape devices. In terms of feature set, it is similar to the HAB. The documentation status is also similar. The application notes are freely available. There is also an excellent documentation of the LSDK, which is SDK for Layerscape devices, which describes how to use the secure boot feature in the chapter 6.1, which is named Secure Boot. To get the reference manual and the signing tool, the registration is also required. Now we will talk about the Malware Armada SoCs. The details about the secure boot feature in that case are not publicly available. The SoC reference manual and secure boot application note require an NDA to get them. Despite the lack of documentation, you can find some useful information in the malware GitHub repositories. Specifically, the trusted boot text file within the U-boot repository provides almost step-by-step guide how the secure boot can be set up. You can learn that the secure boot process is similar for Armada 38X and Armada 7K or Armada 8K families. The fusing command is present both in U-boot shell and in EDK2 UEFI. And the signing tool can be found in the ATF malware repository at the tools do image location. The ST has entered the Linux market a while ago with the STM32MP1 SoC. It also provides a secure boot feature. Unlike others, in this case only the EC keys are supported, not RSA. The high-quality documentation on the secure boot feature and how it can be used is available online. The key generation and key signing tools and are part of the STM32 Cube Programmer Toolkit, which can be downloaded after a free registration. Another interesting example is the Xilinx. The secure boot in that case supports the RSA 2038-bit keys. It is perhaps one of the most open vendors when it comes to the documentation, as the reference manual and secure boot documentation can be downloaded even without registration. The application note describes the secure boot process presentation in great details. You could also learn more about the secure boot from technical overview in the technical reference manual, which is in the chapter 32, Device Secure Boot. The next one is NVIDIA with its Tegra SoC family. The secure boot in that case uses the 2038-bit RSA keys as well. The online Jetpack SDK documentation provides all of the details you would need to implement the secure boot on NVIDIA devices. The keys are simply generated using OpenSSL command line. The fusing and signing tools are part of the Jetpack SDK. The ODM-fuse script is used to program the fuses, while the flashing script has option for binary signing as well. In case of the microchip, we have analyzed the SA-MA5 SoCs. The secure boot feature is also there, but the publicly available documentation is missing some details of it. There is some more documentation which requires an NDA with microchip to obtain one. There is also a secure variant of Samba tools, which is used for code signing and fuse programming. Its usage is described, but the tool itself requires the NDA as well to receive it. We cannot say much about the secure boot in the TI-CTARA SoCs. The public documents only mention that the secure boot feature is there, but provide not that much details. The high-level secure boot overview is truly high-level. It can be treated more as a marketing material rather than technical documentation. In order to receive more details, contact with TI representatives is necessary. Qualcomm also provides only the high-level documentation in terms of the secure boot feature. But we can learn some interesting stuff from third-party write-ups, such as the Timesys blog or the Lineage OS blog. For example, we can learn that the signing tool is called the SEC tool, and it requires the NDA to receive one. Rockchip is one of the most popular Chinese SoC vendors. There is not much documentation out there. The technical reference manual mentions that the secure boot and FUse features are there, but it is not clear how it could be used. Some more documents can be found online, like the Rockchip secure boot specification. We can definitely learn from there that some Windows tools called secure boot tool exists, and it is used for signing firmware binaries. So in terms of Rockchip, most likely there is some kind of secure boot, but it is not clear how to use it. We also couldn't find any success stories about that feature. Contact with vendor would be required in that case. Another one of the popular Chinese SoC vendors is the Allwinner. There are some signs that some form of secure boot feature is there, but possibly no one knows how to use one. Some details can be found online, for example in the ARM forum. Specifically, one of the most advanced user stories can also be found there, but it got stuck at some point. The results of research are presented in the following slide. We can see that out of 11 analyzed cases, the secure boot could be used without any form of NDA in 6 of them. An interesting case is the Marvel, where the documentation requires NDA, but the information and tools from the GitHub repositories should be enough to implement a secure boot flow in your device, maybe without fully understanding all of the details. Also, most vendors require at least free registration to get access to some of the documents and tools. Some comments to the table from previous slide, which we have already covered. And finally, we have reached to the summary. After this research, we can say that the general implementation of secure boot is similar across vendors. The main idea is to verify the image before execution. The public key is usually stored in the FUse registers, and a specific FUse needs to be set to lock the device. Most commonly, the RSA 2038 key type is used as the signing key. In some cases, only the EC keys are supported, and in some cases, multiple key types are supported. In all cases, the SHA-256 is used as a hash function for digital signature. Usually, also the firmware decryption feature is present, but it was not in the scope of our presentation to discuss one. Feel free to contact us if you believe we can help you in any way. We are always open to cooperate and discuss. And now, question time.